All right, we're looking at ACT worksheet 214, sequences. Um, Out of 60 problems, maybe 1 to 2 will be sequences. These problems can range anywhere in difficulty from some of the easiest problems on the test to some of the hardest ones or most difficult. I'll take you through everything you need to know. You will definitely need to be able to differentiate between what an arithmetic and what a geometric sequence is. If that doesn't sound familiar, don't worry. I'll show you exactly the difference between the two. I promise you that you're already familiar with both concepts. You just don't know it yet. You will have to be able to calculate the nth term or the certain term in sequences. And then there's a really popular problem that the ACT loves. It's this repeating pattern problem in a sequence. And I'll show you what that problem is and what it entails. And then finally, I'm going to finish up with a rare problem that tends to be on the scope of the most difficult for sequences. So we'll finish up with the hardest thing you'll see, and I'll show you how you'll do it. So that said, let's kind of go through this. So an arithmetic sequence is when you're counting by the same number in a pattern. So if I say 5, 8, 11, 14, you can probably go, oh, the fifth term is 17, and you'd be right. So arithmetic is when you're counting up or counting down by the same number, okay? So the question would be, it was easy enough to get the fifth term of the sequence, but what if they wanted the 90th term, right? What if they wanted the 90th term of the sequence? Well, there's a formula for this, and your chances of needing to know it on the test are less than 50%, but you probably want to be safe. So the formula is fairly intuitive. The way it would work with this sequence is we take whatever the first term is, so 5, and then we add what we're counting by. We're counting by 3, and it's times whatever term we want minus 1. And that can get us any term in the sequence. And if you think about it, this makes perfect sense. And I love T-charts. If you've watched these other videos, you know I'm all about the T-chart life. So anyway, n is the term, and then this will just be the output for the value. And if you think about this, if I put in 1, so if I want the first term, I'm going to get 3 times 0 plus 5. I'm going to get out 5. If I want the second term, well, if I put in 2, I'm going to get 1 times 3, right? 3 plus 5, and that's going to be 8. And so on. Every time n goes up 1, I multiply by 1 more 3, so I'm counting up by 3. So if I wanted the 90th term in the sequence, I would put 90 into the n spot, and I would have 5 plus 267, and I'd get 272. So that's the concept behind an arithmetic sequence. You're counting up or counting down by the same amount. Very similar to a linear equation, if you think about it. It's a consistent interval. And you can see that in the T-chart. Like if I were to put in the third term, we would get out 11. And as you see, we rise 3, we run 1 almost, is another way you can kind of think about it. Anyway, let's look at geometric sequences. I promised that I would explain both, so I'm making good on that promise. So a geometric sequence, well, we have 4, 12, 36, 108. This one's probably a little harder to figure out the next number, but you notice that I'm multiplying by 3. The next number would be 324. So geometric is you are multiplying by the same amount. And it could be multiplying by a fraction. We could conversely, if we're multiplying by 1/4, we could be looking at 324, 108, 36, 12, and 4. We could go in reverse if our common factor, that's the word that's used, common factor is 1/4. But in this case, our common factor is 4. So just like before, what if they want a much higher term in the sequence? They don't want the fifth term. They want, in this case, I said the 15th term because I realize it's going to go up really fast. Well, the way you do it is you take, let me actually zoom out so that you can see the original problem. And that way, okay, so you can see this original sequence and you can see this down here. So what you do is you take the first term, just like in arithmetic, you put the first term there. But because we're multiplying by 3, not adding by 3, it's going to be times 3, but it's going to be your term minus 1. So again, T-charts are kind of helpful to visualize and see things. N is the input term, and then this is the output. So if you were to put in 1, you'd have 3 to the 0, which is 1, so you'd get out 4. So put in 1, get out 4. If you were to put in 2, you'd have 3 to the first, 3 times 4, 12. So you notice you're multiplying by 3. So there's the first term and there's the second term. If you were to put in 3, then you have 3 squared, which is 9, because it's 3 minus 1. 9 times 4, 36. And what you notice is that you're multiplying by 4. So some of you may recognize, hey, wait a minute, if I'm multiplying by the same amount every time, it's just like an exponential equation. And in fact, it is. The geometric is set up like an exponential equation where your input value is in the exponent or indices spot, and you're multiplying by a common factor. So anyway, do you need to have this memorized? Maybe not for the test, but again, I would err on the side of just knowing it. It's more likely to be in your favor if you know it and understand it. And it's pretty intuitive. Anyway, here's this repeating pattern problem. And this type of problem is really common on the test. Not to say it will show up on your test, but I wouldn't be surprised if it did. So let's look at this example. And feel free to pause the video if you want to try it on your own first. In fact, I'll scroll up so that you can't see the answer. So we have this repeating decimal. That's what this bar means. And it wants to know what's the 91st term to the right of the decimal. So we're repeating in 4s. So if you think about it, if I said not the 91st term, but I just said like the 9th term, let's say, we'd be going 0.6572, 6572. So you know the 9th term would be a 6. So what's the quick way to figure that out? Well, I'll show you. What you do is you do 9 divided by 4. And because 4 is, how many digits we're repeating. And you'd realize, okay, 4 goes into this twice, but I have a remainder of 1. And the remainder tells you everything. Really, if you divided it, you would get 2.25, right? If you divide 4 into 9, you get 2.25. And 0.25 of a pattern of 4 is a remainder of 1. So if you think about it, whatever your decimal is, that can tell you what your remainder is. The minute you know your remainder, you know how far you count into the next sequence of the problem. So we have the first sequence, the second sequence, and then we're 1 into the third sequence. So the digit would be 6 if they wanted the 9th term. So feel free to pause now even and see if you can figure this problem out. I'm going to keep on going though. So again, if we have 91, and we divide that by 4, we're looking at, well, we know 4 times 20 is 80, so 4 times 22 is 88. So we're going to go in 22.75 times, right? So that means we're really going 22 times with a remainder of 3. So that would mean we just finished the sequence and then we go 3 into the next sequence after it repeats 22 times. So the sequence would repeat 22 times, then we'd go 3 into the 23rd time. So we'd go 6, 5, 7. So 7 would be our digit. And here it is, 7. Okay. So hopefully that makes sense. We'll do one of those in just a moment. Let's go down to some of these test problems. I picked some of the harder ones on the packet. Okay. So really, hopefully my explanation was good enough. You should be able to pause the video and do 8. Real easy. If you don't feel confident though, I'll kind of run through it one more time. So the repeating decimal is 3 digits. It's 578, and we would know the 85th term. So what we would do is we would do 85 divided by 3. So if we think about that, 3 times 30 is 90. So 3 times 28 is going to be 84. So essentially, this is going to go in 28.3 times, or 28 times with a remainder of 1. So if 1 is our remainder, then we're going to finish the repeating pattern 28 times. It's going to repeat 28 times, and then we go 1 into the 29th time. So 5 is going to be the number as we go 1 into the 29th time. Okay. Uh, 16 is a much harder version of the problem we just did. So again, it's a repeating pattern problem. However, it's a clever version of it. This would come within the last 10 of a test. Feel free to pause the video and take a crack at it. I'm just going to keep on going. So if you think about it, 7 to the first is 7. 7 to the second. By the way, there's no way that if you try to put this in your calculator is going to bust. The calculator's going to be like, what are you doing to me? Just don't talk to me anymore. So there's got to be a different way to figure this one out. So what we're doing is we're looking to see if there's a pattern. So 7 squared is 49. 7 to the third, if you know that off the top of your head, great. I think it's 349. 7 to the third, 343. Good thing I put that in the calculator and didn't try to be the hero. 7 to the fourth, 2401. Now here's where things get interesting. 7 to the fifth is going to be 16807. 7 to the sixth, and hopefully you're noticing a pattern here, is going to be 117,649. 7 to the seventh, 823,543. You can probably guess what 7 to the 10th is going to be. Our ones digit is going to end up being a 1. And try it in your calculator if you don't believe me, or even if you do believe me. So we get 5,764,801. Okay. What you notice is that we're repeating in a sequence of 4, right? So the ones digit is just following the same pattern in a sequence of 4. There's a reason for this. I'm not going to go into it in this video because I know that we're kind of tight on time, but think about if you're multiplying the ones digit every time, the only thing that's going to impact the next thing is, so 7 times 9 is 3, 9 times 3 is, hold up, I'm mucking that up big time. Why am I mucking that up? 7 times 9 is 63. That puts that there. Oh, 3 times, no, not 3 times. Oh, 3 times 7 is 21. That puts a 1 there. Multiply the 1 by 7, you get 7. Multiply 7 by 7, you get 49. There's a 9. Anyway, I did a terrible job of explaining that because I kind of didn't want to spend time on it. So you can almost forget that part of the video. My apologies. But feel free to play around with it to better understand why. But anyway, we know it's a pattern of 4. We know it's a pattern of 4. Because we know that, we just do 126 divided by 4. And when we divide 126 by 4, we get 31.5. What does that mean? That means that this pattern is going to repeat 31 times, and then the last time it's going to go 2 deep. So we're going to go to the 9, right? Awesome. Okay. This one. So this one you should be able to get if you remember the bit on arithmetic sequences that I gave you at the top. So the third term is 13. Fourth term is 18. It's an arithmetic sequence, which means we're counting. So we're counting by 5. So this is going to be an 8. This is going to be a 3. It wants to know the 50th term. So the easiest way to do this is to say the first term is 3. And then we're counting by 5s. And then n minus 1. So for the 50th term, essentially all we're doing is we're saying we have a 3. And then we want, with this 3, we want to add 5 49 times. That's what the back half is saying. Right. We're going to take the 50th term. The first term is 3. And then 49 times, we're going to add 5. So if we do this, 5 times 49 is 245 plus 3 gets us 248. So A. Okay. Last but not least, I promised you a pretty hard problem. This is a hard problem. There's going to be a little bit of an explanation with it as well. Feel free to pause the video, though, and give it a go. But I'm going to keep on going. So sometimes you get this. You get a problem where, so it says the sum of the first 30 positive integers is 465, which of the following is the sum of the first 60 positive integers. So if they want to know the sum of all the integers in any type of sequence or pattern, there is a pretty simple way to do it. What you would do is, so actually, let me kind of demo it on a small one. So say we have the numbers, I don't know, 3, we'll count by twos, 5, 7, 9, 11. Okay. We know the sum of this to be, these are going to add up to 14. These are going to add up to 14, and then we add another 7, right? So like the outer ones add up to 14. These add up to 14. It's all going to average to 7 in the end. But what we get is 35 would be the sum, right? 14 twice plus 7. But the official way to do it is if you think about an average problem, or maybe not the official, but a more official way to do it. You have average equals sum of the terms divided by number of terms. Okay, so if we think about this, what does that mean? That means that the sum of the terms is the average times the number of terms, right? If we just move number of terms from the bottom. So the way we would apply it to this is the easiest way to get the average of any sequence is just because we're counting away from the 7 by the same amount. The average of the 5 and the 9 would be 14. The average of the 3 and the 11 would be, the average of the 5 and the 9 would be 7. The average of the 3 and the 11 would be 7 because we're counting out by the same amount. So it's all going to average to 7, right, if we're counting by the same amount away and towards the middle term. So if you think about that, then the first plus the last term, so to get the average, just think first plus last divided by 2. Just take the average of the first and the last term, and you'll have the average. The number of terms is a little trickier. In the case of this one, we're counting by 2. What you would do is you take the difference between the last and the first term. So last minus first. Divide by what you're counting by, in this case 2, and add 1 to that. Okay, I'll explain exactly why that is the way it is. Let me zoom out a little bit. So the first and the last term of the sequence is 3 plus 11 divided by 2. That gets us 7, so our average is 7. First, last term, so last is 11. First term is 3. You take the difference between those two. You have 8. 8 divided by 2 is 4. You add 1 to 4, right? This whole thing is 4. You add 1 to 4, and you're going to have 5. So the reason why that works is if you think about it, we're counting by 2s from 3 to 11. So if we take the difference, it's 8. We have to count 2 into 8. So 2 would go into 8 4 times. So that accounts for counting to the 5, the 7, the 9, and the 11. What it doesn't account for is the 3 that we started at. So if you take the last term minus the first term, you get the difference. You divide it by what you're counting by, and that will get you the number of terms you've counted out to get to the last term, and then you just add 1 to include the first term back in. If that makes sense, great. If it makes no sense, don't lose any sleep over it. This is a very rare type of problem, and it would be one of the last problems on the test. But anyway, we get the sum of the sequence to be 35. If you're feeling confident, give this one a shot right now. Pause the video and see if you can do it. If not, I'm going to quickly do it. So we want that average. So if we want the first 60 positive integers, well, the first integer is going to be 1. The last integer is going to be 60. We divide it by 2. That's going to get us our average, right? So our average is going to be 30.5. Okay. Then we want the number of terms. Well, lucky for us, I mean, we know it's 60 terms, but what you do is you would do, officially you do 60 minus 1, difference between the first and last, divided by what you're counting by plus 1. So that's going to get you 59 plus 160. So if you just do 30.5 times 60, you are going to get the sum of all the terms. So 30.5 times 60, that gets us 1,830. So that's officially how to go about doing that one. In all honesty, though, if you think about it, if you're just logical, it tells you the first 30 terms add up to 465, and then you know that you're adding up much higher numbers. So you know it's going to be way more than just like double, right? You know it's going to be much higher than B. And then depending on your sense of numbers, you may be able to reason between C, D, and E. But anyway, hopefully that helps. Good luck with this, the other problems on the sequence packet. And as always, feel free to return for any other videos. Okay, bye.